4.4 Building quadratic models from verbal description. So in economics, revenue R in dollars is defined as the amount of money received from the sale of an item and is equal to the unit selling price P in dollars of the item times the number X of units actually sold. So all that is saying is R equals X times P. All right, let's maximize revenue. An electronics company has found that when certain calculators are sold at a price of $P per unit, the number X of calculators sold is given by the demand equation. X equals 18,750 minus 125P. Our first thing we need to do is find a model that expresses the revenue R as a function of the price P. So we want a model that is R of P. We want R of P. That's what we're trying to get. What we're given is R equals X times P, and we're also given X equals 18,750 minus 125P. Since we need a quadratic out of this, how do we know we need a quadratic? Because it says maximizing. So we need a quadratic out of this. In order to get a quadratic, we're going to use substitution. So we're going to plug X, which is the demand, into the revenue. Because if you think about it, how much money you make, isn't that out of how many people buy your product? So that's the demand. That's why we plug demand into revenue, because without a demand, we don't get any revenue. So we're going to plug it in. We have R of P, wrong color. R of P equals X, and the X we're plugging in is 18,750 minus 125P, all times P. Anytime we usually see parentheses, we're going to distribute. So when we do, we have R of P equals 18,750P minus 125P squared. We can go ahead and rewrite that to make it look better. You don't have to, but I like to rewrite it because I like to see the squared first. And now we have our model. So we do have a quadratic. We have a quadratic because of the little 2. So since we have a quadratic, we can go ahead and find maximum revenue. But before we do that, let's go ahead and answer part B. What is the domain of R? So domain, that always represents your X values. So X in this example stands for number of calculators sold. So calculators sold, that's X. Can we sell negative calculators? No. Can we sell 0 calculators? Technically, but you can't sell negative. That's impossible. I can sell nothing, but I cannot sell negative things. In the real world, I can't sell negative things. So we need to know what's going to make X greater than or equal to 0. And selling comes from the demand. So from the demand, we want to know what makes the demand greater than or equal to 0. So we have our demand equation. So it's always going to be demand greater demand greater than or equal to 0, because we want to know how much can we sell it for to make it greater than 0. So we have our demand equation, which is 18,750 minus 125P is greater than or equal to 0. We're going to solve for P. So let's add 125 over. So when we do, we have 18,750 equals 120, is greater than or equal to 125P. Divide by 125 to each side, and we get 150 is greater than or equal to P. Let's rewrite that. So you see how it's pointing towards P, so it should always point towards P. Okay. 150. So our domain is 0 to 150. And remember, those are our x values. You can write it in set notation as well. You can say x such that 0 is in between our less than or equal to x, and that's less than or equal to 150. Alrighty. Part C, what unit price should be used to maximize revenue? Let me go back to domain real quick, just to kind of explain that more. Domain, what we found is what's the least and most price someone's willing to buy this for. So they're willing to pay $0 to $150, not a dime more. Alright, part C. Part C is asking what unit price should be used to maximize revenue. So we see that word maximize. Anytime we see that with a quadratic, you know we're talking about the vertex. The vertex, remember, that's x and y. But instead of x and y, in this word problem, we're going to be using p and r, because that's in place of the x is p, in place of the y is r. So if it's asking for what unit price, we're technically looking for the p of the vertex. So let's go ahead and find the p, or the x, sorry, that's huge, or the x of the vertex. So we have x equals negative b over 2a. Using the quadratic we found, that's in green. That's how we're going to find our vertex. So negative b, which is 18,750, minus, or over 2 times negative 125. So when you plug that into your calculator, we get 75. That means x, which is p, is $75. Now, what did we just find? If you want to maximize revenue, so to maximize revenue, each calculator should be charged, or each calculator should be sold for $75. So if they want to get the most money they can, they're going to sell this calculator for $75. And then everyone's going to buy it. Think of it. When you're on Amazon shopping, when something's too cheap, you're not going to buy it because you're like, I don't know, seems weary, right? And if something's too expensive, you're like, no, I'm not going to pay your money for that. You go towards the middle one. That's why they charge that price, because more and more people are going to buy it. Alrighty, part D. If this price is charged, what is the maximum revenue? So since, we see that word maximum, we're talking about vertex, but we're looking at maximum revenue. So we found the price we're going to pay at $75. Now we're going to plug it in. We're going to plug it into the quadratic we just found in part A, which was the R of P. So let's go ahead and plug in P, because remember that represents P because it's price. So we have revenue equals negative 125 P squared plus 18,750 P. Do you notice every time I say that variable, I leave a space and then go plug it back in after? It's a great habit to get into. So you plug it into your handy dandy calculator, and we get 703,125. So what that means If they charge $75 per calculator, they will earn a maximum revenue of $703,125. Okie dokie. Part E, how many units are sold at this price? Okay, so what price are we talking about? What are we talking about here? The price of $75. Because that's the price we found. And when we're talking about how many units are sold, how many units sold is the demand. And we know the demand equation. It's x equals 18,750 minus 125p. So that's what we're going to do, is we want to know the demand if we charge $75. So we have 18,750 minus 125p, and our p is 75. Plug it in, and we get the demand of 9,307. Oh, wrong way, place to put the comma. 9,375 calculators sold. So they will sell 9,375 calculators if they charge $75. All right, part F wants us to graph. So this is a real-world application because we're talking about money, we're talking about revenue, we're talking about selling goods. The real world only happens in quadrant 1. Like applications like this, real world. When you talk about engineering and physics, we use the other quadrants because it helps us decipher things with satellites and stuff like that. I'm not going to get into it. But when we're talking about money and revenue and real world, like super real world with money and stuff like that, we're going to be using quadrant 1. So in quadrant 1, we want to first plot our domain. So you remember that domain we found of 0 to 150? And remember, domain are x's. So the domain for x's, it stands for price. The y stands for revenue. So the maximum and minimum price, or the domain, is 0 to 150. We have other values. We found the vertex. The vertex is 75, 700,000, 125. So that means the max we can earn is 703,125. And we earn that much when we charge $75. Do you notice 75 is right between 0 and 150? Just throwing that out there. So we have our vertex right up here. Right there. And from here, we're just going to connect the dots. And there's our quadratic. Now, why is revenue quadratic in form? Because if you charge too much, less people will buy it. If you charge too little, you won't earn enough money. So that's why it's quadratic. Alrighty. Part G. What price should be charged for the product to collect at least $590,625 in revenue? First, you need to make sure that's possible. Is it possible to make $590,000? Yes, because the maximum amount of money, why am I stressing this? Oh my gosh, just really write this down. The maximum amount of money we can earn in this problem is $703,000. So it's totally possible to make $590,000. So since it's possible, we are allowed to plug it in for our revenue. So part G, it's asking us what price will be charged when we have a revenue of $590,625. So we're going to plug it into our revenue quadratic that we found. And the quadratic we found was the negative 125p squared plus 18,750p. So we're going to plug it in for our revenue. Since this is a quadratic, we need to make sure everything equals to 0. So we get 0 equals negative 125p squared plus 18,750p minus 590,625. I don't know if you noticed, but they all end in a 5 and a 0, so we can take out 125. Let's take out negative 125, though. So when we take out negative 125, remember that's the greatest common factor. We're left with p squared minus 150p plus 4,725. Now we need to factor this. Also, just in case you don't know, you could use this, or you can use this and plug it in the quadratic formula. If you don't want to factor, you can plug either of these into the quadratic formula and still get the same exact answer. But I like to factor. It's one of my favorite F words other than fractions. So when we factor, we're going to set each of these equal to 0 after we factor. So we have 0 equals negative 125 times p minus 105 and p minus 45. So we have 0 equals negative 125, 0 equals p minus 105, and we have 0 equals p minus 45. So here, this means nothing. 0 equals negative 125. Okay, that's nothing. Next, we have 105 equals p, and 45 equals p. So they can charge $45 or $105 and earn $590,625. So let me explain that with our graph. So the max revenue is the revenue we're trying to find is 590,625. So we can say that's about right here. So if we go across, you see how it hits twice, and where it hits is at 45 and 105, because that leads into, if I charge $45, people will buy more, but I need more and more people to buy to make enough money, because I'm charging not enough money. And if I charge too much, no one's gonna buy it. So a farmer has 2,500 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So let's just take out what we know about rectangles. So we know that rectangles, they look something like this, and they have 2 x's and 2 y's. I mean, they do have 2 lengths and 2 widths, but in this case we're going to use x and y because we're talking about like algebra, which is x and y. And then we also know formulas to do with rectangles. We know perimeter is 2x plus 2w, and then we know area is base times height, which is just x, my bad, I meant to put y there, 2x plus 2y, and we know area is base times height, which is just x times y. So those are the 2 formulas that we should associate with rectangles every time. So perimeter, that's around. Around means to enclose. So we have 2,500 yards of fence to enclose whatever this is. So we know we need a quadratic out of this. How do we know we need a quadratic? Because it says most area. Remember, most, that means maximum. So we want to know what can we do to maximize the area. So we need to plug it into A equals x times y. We're going to plug it in to y. So we need to solve for y. Now, why do I choose y? I chose y because don't we like to see x in the problem? So that's why I want to keep it in the problem. I don't want to solve for x. I want to keep it in the problem. So in the perimeter equation, I'm going to solve for y. I'm going to do that by subtracting 2x. So we have 2,500 minus 2x equals 2y. And then we need to divide everything by 2. So we divide every little piece by 2. So 2,500 divided by 2 is 1,250. 2 divided by 2, we just get 1, and that equals y. So that's what I'm going to do. I'm going to take this y equals and substitute it in for y. So we have area equals x times y, which is 1,250 minus x. We're going to distribute, and we have a of x equals 1,250x minus x squared. We write a of x because that's the function we're working with. We're working with area, and the variable we're working with is x. I'm just going to rewrite this to make it ax plus b. So we have negative x squared plus 1250x. I rewrite it because we like to see x squared first. Alright, so now that we have our quadratic, we can figure out the most area. And remember, most, that's already hinting at the vertex. So our vertex is negative b over 2a, so negative 1250 over 2 times negative 1. So we have negative 1250 divided by negative 2, and we get positive, let's see what I get. 625, there it is. I don't have my calculator with me, so 625. So that's what x is 625. So that's exactly what x is. I can actually put it in here for 625. We found x. So yes, we're going to find y, don't worry. And you're probably saying I can just use the perimeter to find y, and that's what we'll do after on. So we are still trying to find the most area. When we have the vertex, we need to plug in x. So we're going to plug in as x equals 625, and we're going to plug it into the quadratic that we came up with. So we'll have area equals negative x squared plus 1250x, and the x we're plugging in is 625. We can simplify this using your calculator, and when you do, we get 390,625. So 390,625. So that is the area, is 390,000. That is the area that we can do. But we still need to find the dimensions. So after we find the area, to find the dimensions, I'm going to bring down the perimeter problem again. So the perimeter is 2,500 equals 2x plus 2y. And we have x, it's 625. So we have 2,500 equals 2 times x plus 2y. So 625 goes in there. And we have 2,500 equals 1,250 plus 2y. So we subtract it over. We'll have 1,250 equals 2y. Divide by 2. And we get 625 equals y. So coincidentally, this is a square, but we didn't know that. But so our dimensions are 625 by 625. So to write this out, we would say So the largest rectangle that can be enclosed with 2,500 yards is a fence has an area of 390,625 yards squared, and its dimensions are 625 yards by 625 yards. The question on the test is just like the review. Instead of though for here, it'll be p equals x plus 2y. So what's on the review is going to be on the test. All right, this is the bonus question. So the Golden Gate Bridge, a suspension bridge, spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from two huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. Find the height of the cable above the road at a distance of 1,500 feet from the center. Okay, we need to draw this out. So to draw this out, we have here, that's the road, because it's a flat surface, it's just a road. And then we have towers. Those are the towers that hold it all together. And then it tells me the cables create a parabolic shape. All that means is it creates a parabola. And that looks like a portion of the Golden Gate Bridge, right? Like if you took a chunk out of it, that's what it looks like. All right, they gave us a bunch of information about this. They told us that the towers are 746 tall, or 746 feet tall. So the tower from here to here is 746 feet, and that's the same on the opposite side. Oh, my bad, I forgot to draw the water. Gonna start this over. Forgot to draw the water. Duh. The water is right here. Alright, there we go. There we go. So go ahead and blah, blah, blah. Let's start over. Alright, so we have our towers, and we have our water, and then the towers from here to here are 746 feet tall. Because if you think of a bridge, don't the towers go into the water? Because that's how they hold it up, right? And then it's saying that the road, it's 90 feet wide. Okay, I don't care about that. I don't care how wide the road is. But it says the road is 220 feet above the water. So the road to the water is 220 feet. Isn't that crazy? You're just 200 feet above the water when you're driving on the Golden Gate Bridge. I've always wanted to drive it. Alright, now it's saying a whole bunch more information, that it creates a parabolic shape at the center of the bridge. So if I wanted to continue drawing this as an X and Y chart, here's our Y's. So this is the center of the bridge, which is 0, 0. We can find how tall the towers are on the road, right? We can find this distance. We can find that distance by subtracting. So we do 746 minus 220, and we get 526. So the distance from the road to the top of the tower is 526 feet. And then it also says that the towers are 4,200 feet apart. So that means from the left tower to the right tower, it's 4,200 feet. So if we have two sides of the towers, 4,200 divided by 2, we get 2,100. So from here to here, actually, let me move that in a better spot. So from here to here, it's 2,100 feet. And that's the same thing for here to here is 2,100 feet. Now it's asking, find the height if the distance from the road is 1,500 feet. So what we're talking about from here to here, let's say that's 1,500. What's the height? So we're trying to find this spot right here. So 1,500, and we want to find the y, the height. Remember, height is always y. All right, so we drew everything. Now we know quadratics are y equals ax squared. And we could have the plus bx plus c, but that's a quadratic. It's ax squared. We do have several points because we don't know what this quadratic is, so we need to find it. We have points. Don't we have a point at 526 and 2,100? Because isn't this the x distance? So we have x equals 2,100. And then don't we know the height right here? Look at my pen. So isn't that height from the road to the top 526 feet? So we have y equals 526 feet. And we're just going to plug it into our formula of ax squared. So we have 526 equals a times x squared, and x is 2,100. I'm not going to simplify this. I'm actually just going to divide it out. So I'm dividing out 2,100 squared. So a is 526, that's a 5. Let me rewrite that. 526 over 2,100 squared, and that equals a. I like to keep it like that because, trust me, it is so much easier to work with like this. Okay, so that's what our a is. Let's plug it back into the equation. We have y equals 526 over 2,100 squared and times x squared. Alrighty. So now that we have our equation, can't we find the y if we have x? So they're saying if x is 1,500, what's y? So let's plug in 1,500. So we have y equals 526 over 2,100 squared times 1,500 squared. Please plug this into your calculator exactly the way it looks, and when you do, we get 109.3 feet. So what we just found was the cable is 119.3 feet above the road at a distance of 1,000 feet from the center of the bridge.